Hello, everyone. Today's lesson is about the effect of orientation on polymer properties. In this lesson, we will study the impact and principles of polymer orientation on polymer properties. By controlling polymer orientation, we can largely customize and optimize the comprehensive performance of materials to meet the demands of specific application scenarios. Orientation technology is widely applied in the processing and modification of plastics, fibers, films, and in other polymer materials. After orientation, the general characteristic of polymers is their anisotropy in performance. Before orientation, the arrangement of macromolecular chains and chain segments is random, which leads to isotropy. After orientation, due to the intermolecular forces along the orientation direction being primarily chemical bonds, and the intermolecular forces perpendicular to the orientation direction being primarily van der Waals forces, anisotropy is exhibited. This results in significant differences in the mechanical, optical, and thermal properties of the material before and after orientation. The specific effects of orientation on high polymers include, but are not limited to, the following aspects. First, mechanical properties. Orientation leads to an increase in the overall elastic modulus of the material. This is because the intermolecular forces are enhanced after orientation, making the molecular chains more resistant to further deformation. After orientation, different directions show different changes in performance. In the orientation direction, the tensile strength, flexural strength, and modulus of the high polymer typically increase significantly. This is because the molecular chains align neatly along the stress direction. This forms a more ordered structure, which can more effectively transmit stress. However, the mechanical properties perpendicular to the orientation direction often decrease. This is because the molecular chains are more disordered in this direction. For uniaxially oriented films, the tensile strength in the orientation direction is very high. It is not easily damaged. However, the tensile strength perpendicular to the orientation direction is lower. Even slight stress can cause damage. For amorphous high polymers, the elongation at break in the orientation direction may increase. For crystalline polymers, the elongation at break may decrease with increasing orientation degree. This is because orientation strengthens the connections in the crystalline regions, making the material harder and less stretchable. Second, effect on optical properties. Orientation causes polymer chains to arrange differently along different directions, which leads to the phenomenon of birefringence in high polymers. That is, the speed of light propagation through the material differs along different directions. This property is of significant application value in optical films, polarizers, and other applications. Third, effect on thermal properties. Orientation increases the glass transition temperature of the material. This is because the oriented structure restricts the motion of the molecular chains. For crystalline high polymers, orientation can also induce crystallization, which increases the crystallinity and density of the material. Thus, it broadens the material's service temperature range. Fourth, effect on dimensional stability through orientation treatment. Especially by axial orientation, dimensional stability of high polymer materials can be significantly improved, reducing shrinkage deformation during use. This is especially important for synthetic fibers and film products. The degree of shrinkage deformation after molding of oriented polymers is proportional to the degree of orientation. For uniaxially oriented polymers, the shrinkage deformation perpendicular to the flow direction is usually larger than that in the orientation direction. This is because the molecular chains are stretched along the orientation direction, resulting in smaller volume change in that direction. Fifth, effect on other properties. Orientation may also affect the material's electrical properties, gas permeability, and chemical resistance, etc. This depends on the orientation method and the inherent properties of the high polymer. To summarize this section, polymer orientation has a significant impact on its properties. Thus, orientation technology is widely applied in the processing and modification of plastics, fibers, films, and other polymer materials. After orientation, the performance of polymer materials exhibits anisotropy both along the orientation direction and perpendicular to it. This results in significant differences in mechanical, optical, and thermal properties before and after orientation.